Next, let's look at circular polarization. So let's apply a different criteria. Instead of being a function of m pi, we're going to say, well, first of all, for it to be circular, we're going to say that ex and ey are both the same number, which I'll call e naught. So the x component and the y component are the same. And then secondarily, phi has to be some phase shift of plus or minus pi half. Now note that when I say plus or minus pi half, I'm also referring to that if this phi, if it was given to you as some giant number that's not between minus pi and plus pi, that you would bring it into the range of minus pi and plus pi by adding or subtracting any multiple of 2 pi in order to get it in that range. So once you've done that simplification, if you find that ex and ey are both the same, so these two are the same amplitude, and the phase difference is exactly some multiple of pi half, or is exactly pi half once you've done that minus pi to plus pi range simplification, what does that mean that this value is? That means that this is j, right? If it's pi half, then it's j. If it's minus pi half, then that means it's minus j, right? So that means that for a, let's just stick with a z propagating wave, you're able to rewrite this as e naught x hat plus or minus j e naught y hat, right? And then your propagating factor, e to the minus j beta z. Let's just assume it's lossless for now, so we won't worry about the alpha. So if we were to do that, let's just bring back the instantaneous form just to take a look at what that looks like. So to do the instantaneous form, you would multiply by e to the j omega t and take the real part. So you'll find that you get e to the cosine of omega t minus beta z for the x component, and then e naught cosine of omega t minus beta z plus minus pi half for the y component. And remember that if you do plus minus pi half, you can also rewrite this as positive or minus sign, right? So in the case of whether this is plus or minus j, you can rewrite this as the instantaneous form as e naught cosine of omega t minus beta z in the x hat direction minus plus, meaning if this is plus j, you have a minus here. If this is minus j, you have a plus here. E naught sine of omega t minus beta z in the y direction. So let's see what this looks like. Let's try to visualize this. So let's just look at the z equals 0 plane. So I'm sitting right on this xy plane here and watching the wave come right at me. Or it's propagating in the plus z direction, so I'm just sitting right here on the xy plane watching this come right at me. So if I set z equals to 0 into this instantaneous form, I get e of 0 t is going to be equal to e naught of cosine of omega t in the x hat direction minus plus sine of omega t in the y hat direction. Now if you plot this, this is for phi is equal to plus or minus j. So if the phi in this expression is plus j, you had a minus sign. If it's minus j, you have a plus sign over here. And now what does that look like? If you dig deep back into grade school and you were learning about parametric equations, right? That ends up looking like a circle, right? If you have that ends up looking, if you're sitting here, you have your x, y, and you're trying to plot this. If you're trying to plot this expression here, what you end up seeing is that this piece just ends up rotating. So in this drawing here, the y component is sine of omega t, and the x component is cosine of omega t. And if you run this through your head, what you're going to find is that if phi is equal to plus pi half, which is the minus sign situation, you end up with clockwise. And if phi is equal to minus pi half, you're going to end up with counterclockwise. And so one way we describe which direction it rotates, and for this circular polarization, is we often say that it's either right hand or left hand circularly polarized. So you can imagine what that means. So the right and left hand polarization means that if you stick your thumb in the direction that it's traveling, so in this case, if it's traveling in the z direction, you hold your thumb so that your thumb is coming out of the board and curl your fingers. If your right hand fingers curl in the direction of the linear rotation, of the circular polarization rotation, then you say it's right hand polarized. Similarly, if you have your left hand fingers curling and pointing in the direction of the rotation, then you say it's left hand circularly polarized. So let me just summarize the process. So first of all, you get into this phasor form, and if it meets both of these criteria here, then that means that phi is going to be either plus or minus pi half, or this is going to be plus or minus j, right? And so if it's propagating in the z direction, and and the electric field is projected in the x and y hat direction, then a phase of plus or minus pi half means that EY is going to, if it's plus pi half, that means it leads EX. If it's minus pi half, that means it lags EX, which means that the phasor ends up going, in the case of if EY leads EX, then it's going clockwise. If it's lagging EX, then it's counterclockwise. And then if you use your handedness to describe, then you would say that it is, if it's clockwise, that would be left hand circularly polarized, and if it's counterclockwise, it would be right hand circularly polarized. So this is kind of a little map to help you navigate through going from getting it into this phasor form that you use for analysis, and determining both the direction, which one's leading, which one's lagging, and what direction the phasor rotates in the xy plane, and the handedness. Now, one thing to point out is that if it's in the negative z direction, you just reverse all of these. So if it's in the negative z direction, then a phi of plus pi half would mean EY lags x, it rotates counterclockwise, and it's in turn right hand circularly polarized. So basically you just if you keep this the same and flip all of these subsequent conclusions, you come up with the result for in the negative z direction. Now, let's use this little bit of space left to talk about elliptical polarization. So as you can see, as we go from linear to circular, we're loosening our restrictions. So in this case, it's a multiple of pi, and these two components are the same. Circular polarization, the two components are still the same. This is phi is now plus or minus pi half. Now, if neither of these criteria, this is an and statement. So if any of these criteria are not met, then it will be elliptically polarized. So what that means is that the phase difference between them is not plus or minus pi half or some multiple of pi, or, so remember this is or because these are both and, right? You have to meet both of these criteria in order to be linear circular. So or these two are not the same, then that means that it's elliptically polarized. So all that same discussion I had about circular polarization stands. It still works. It's just now this cross section is going to be elliptical in its shape. So basically, in that case, the only question that you need to answer is whether it's right-handed or left-handed elliptically polarized. And so this same kind of logic still applies. So assuming that you're in the plus z direction, Again, if it's negative z, then you just reverse the logic. But if phi is greater than 0, that means that EY leads EX. And so in that case, it's left-hand elliptically polarized. And similarly, if phi is less than 0, then that means that EY lags EX, and it's going to be right-hand elliptically polarized.